in the year 1904 for solving the equations, NS equation, and for getting answer related to some question like what is the drag, what is the lift on this flat plate. So what is boundary layer? Boundary layer divides the flow regime into two categories. First one is known as a inviscid fluid flow or irrotational flow, and second one is known as a real fluid flows, where we have a two-dimensional flow, though fluid flow was a one-dimensional phenomena in this figure, and but inside the boundary layer it is a two-dimensional flow, and outside the boundary layer it is a one-dimensional flow having no viscosity. So for case 1, for outer region, the flow can be analyzed without considering the viscosity. Viscosity is assumed to be 0 and it can be solved very easily. And inside the boundary layer, we apply the NS equation for two directional, means x and y direction, and it can be solved. Right. Now in modern days, there is no need to have this boundary layer approach. These can be solved with the help of Fluent, etc. softwares, and in which we need to give just boundary condition. We need not to assume the boundary layer, right. But to understand the concept and its importance, it is very important to still know about the boundary layer. Then only we can understand several phenomena with the help of boundary layer, and we can solve the problem. Now in these two figures, we have a boundary layer. It is not shown on this scale, but it is just shown here that if we have a velocity v, and if we have a velocity v, in this case the velocity is very large. In this case the Reynolds number is approximately 10 raised to 4 in second figure. In first figure, Reynolds number is approximately 10 raised to 2, right. And what is Reynolds number? Reynolds number in case of the flat plate is defined as Reynolds number. It is written as Rex. It is written as Rex. It is in 10 raised to 2. It is rho v x. So in case of pipe flow, we have diameter, but in case of the flat plate, we have x, rho v x divided by mu, viscosity. So we can visualize the boundary layer thickness. When Reynolds number is less, the boundary layer thickness is more, and when the Reynolds number is more, then boundary layer thickness is less. So when we have a less Reynolds number, in that case the boundary layer thickness is more. If boundary layer thickness is more, then what will happen to du over dy? Means there is more space to achieve velocity, so gradient will be less, and here we have very small space, a small distance to achieve the same velocity or high velocity, so du over dy will be very large. When du over dy will be large in the second figure, then naturally it is multiplied by mu, the force will be also very large, right. Now this is the figure which shows us that what happens to the boundary layer when the length of the plate is large enough. Initially, since Reynolds number is defined as rho v x divided by mu, so when x is less, then we have a laminar boundary layer. So up to this point we have a laminar boundary layer, and generally when Rex is equal to 10 raised to 5 Reynolds number, then up to this point we have the laminar boundary layer. From 10 raised to 5 to around 3 into 10 raised to 6, we have a transitional boundary layer, and after this location, when the Reynolds number is more than 3 into 10 raised to 6 generally, then we have a turbulent boundary layer. So we have three type of boundary layer for same velocity, whatever velocity we have at the incoming, the upstream velocity, we have three type of boundary layers. Initially in very small zone we have laminar boundary layer, then we have a transitional, then we have a turbulent boundary layer. Now you can visualize these three velocity profile in these three type of boundary layers. In case of laminar boundary layer, we see that we have very smooth velocity profile where du over dy is small enough. But in this case you see that from very beginning we have very high velocity, and at this point naturally at the boundary surface the velocity, what is the velocity at the surface? V is equal to 0 to satisfy no slip condition. So to satisfy no slip condition velocity should be 0, and as we move away from the boundary solid surface in the transverse direction, then velocity is large. If velocity is large, then the gradient is very sharp, very high. So that's why the in case of turbulent boundary layer the shear resistance is also very large, right. So here we have these two figures. In the first figure it is not on scale, very large distances are shown just to distinguish the laminar boundary layer, transitional boundary layer and turbulent boundary layer. In the second figure it is on scale. You can visualize that the laminar, in case of laminar boundary layer thickness is almost very less. In transitional we have some boundary layer thickness, in turbulent we have little more thick boundary layers.